Hello everyone. Today I'm going to talk about the particle sampling techniques. This has been a long discussion and there were some debates between cleanroom classification and monitoring, and there are a lot of misinterpretation about this subject, so I would like to clear this out. My name is Hasim Solmaz and I am responsible for EMEA operations here in Lighthouse Worldwide Solutions, and I have different responsibilities in different international organizations. One of them is this ISO TC209, which is responsible to write cleanroom standards, which also developed this technical report that I'm going to share with you today, all basics and details. So we will start with the background. I will describe the current status. We will touch a little bit on the classification and also the monitoring part. Then the challenges that we faced in field that lead us to write this technical report, and also the potential solutions that are given by this technical report, also with the experts from the working group with their ideas, and the application examples and a couple of other suggestions that I'm going to complete. First of all, everything started with the background, which was in the online meeting of TC209. By that time, due to COVID, we were not able to do face-to-face plenary meetings. And one of the subject matter experts, the head of delegation from France, John, said that we need to form a sort of ad hoc group to clear out this road for the people who are having difficulties to design their monitoring system, or the people who are not aware of the difficulties, challenges that they are currently having with the monitoring solutions. So this is how everything started for the technical report. Also, we all know that there are physical limitations because of the system that are being developed by the companies, particle counter companies, and also limitations with the area that we implemented. For example, if you are working with the isolators, you have a very limited space to place your sample tube, and also the device itself as a combination of these two. It's not always easy to have your particle counter right under the service area so that you will have one single line to sample all this out. And another thing is the advanced technologies offering us a very small footprint. So in this area, we have to put the device in one side and the sampling will be another. So there will be a long tubing with the bendings, and the shape is always different with the different applications. So there's no clear document available by that time to show people how to evaluate this risk. And of course, there's a limitation with 5 micron, which also lead in 2015 with the revision of ISO 14644 Part 1, cleanroom classification, especially for pharma industry. 5 micron is no longer available for ISO class 5. Reason is easy because it's not easy always to collect these 5 microns throughout this tubing while you have 29 particles per meter cube. And we always need the longest, shortest time period to get the fastest action possible. So if you lower it down to per minute, you have to find either 1 or 0 particles on 5 micron, which is almost impossible with the tubing system, and there's a technology barrier behind it. This doesn't mean, by the way, the 5 microns are no more important. We always emphasize within our presentations that the 5 microns are quite critical for pharmaceutical applications, and we saw this with the GMP revision. They still have these monitoring parts because we all know that this 5 microns will guide us on the early HVAC system failures, and also with the system design issues, engineering problems, or the wear and tear on our system. This means, okay, 5 micron is not available in ISO class 5, but ISO class 5 is for all industries. For pharma, this is specifically for pharma, this is important for us. That's why we need to have these limitations to be solved with this problem. And there are similarities and differences between classification and the monitoring, so we have to clear this out as well. And the ship kit. Of course, the particle counter manufacturer like us, we are sending this product out for all industries. For example, in nanotechnology industries, electronic industries, hard disk drive manufacturers, they are focusing on smaller particle sizes. And we are shipping it together with 3-meter tubing, where you can use it, for example, in 0.1 micron without any issue. That will be not necessarily a particle loss within the tubing for the smaller size, but when it comes to the pharma applications, most people are directly using this tubing because they said, okay, this has come with the ship kit, so they connect it. So you are seeing this spiral fashion tubing all around the clean room. So this is one of the issue that needs to be cleared out. And placing the particle counter in the right place without interfering with the airflow and causing the turbulence, this is another issue on the background. And unnecessary use of the tripods. This picture, our marketing team create a very nice looking setup. In fact, this is wrong, because if you have this kind of a card, then the best idea is to put directly isokinetic probe on top of it. Even if you are doing it in the turbulent area, most people thought that we need to use these isokinetic probe. In fact, we don't. Because if this is turbulent, then isokinetic probe will not help us to collect particles because the air is turbulent already. So we can even consider having not using these isokinetic probes in turbulent environment because they are all designed for the unidirectional flow conditions. When we say unidirectional, all of these tubings, we will come later, but nice to describe this here. This isokinetic probe design is generally taking this magical number 0.45 meter per second, which means if you have at the height of the sample, if you have 0.45 meter per second flow rate, then this diameter cuts a whole column of air, and which will be enough for it to survive with 28.3 liter per minute sampling. So if it is, let's say, 100 liter, you'll be seeing larger diameter so that this column will be enough to maintain 100 liter per minute so that the air will be cut like a slice and there will be no turbulence. But what if you have, let's say, 0.30 meter per second by safety cabinet conditions? In this case, you'll be making it super isokinetic conditions, the superkinetic conditions, so that your system will work like a vacuum cleaner. That's why the system design, especially we have to take a look at it twice when we are selecting the isokinetic sampling. So there is ISO 14644-1 Annex C. That was one important section which describes saying that, okay, typically 1 meter tubing length is okay. So don't exceed this. But most of the applications in field, people pretend to use the same definition for the monitoring system design. And everybody said, oh, we designed it for 2 meters. We designed it 1.5 meters. How are we going to shorten it? Because there is a limitations on our system design, how we will handle this. In fact, -1 is talking about the classification only, not monitoring. Monitoring is completely a different application. And there is installation challenges, as we mentioned, not limited with the machine, but also in the clean room. You have a service area where you will be providing the particle counters, because also particle counters being accessible for the service requirement is important. You cannot really hide them within the machine where you are not be able to service, so that it will be physically available for you if you need to do any certain servicing, calibration, whatsoever. So this is also a limitation with the installation. And reliable particle data over the time for the alarm and action limits, which means when you collect particles, you shouldn't lose them within the tubing so that it will give you a right indication of the status. What if you have the direct tubing within the system without any particles available in the field? You just touch the tube, you will see a lot of particles coming out from your tubing, right? I'm sure you witnessed the same situation several times. Reason is simple, because even we said, okay, this special tubing is not capturing any particles. In fact, due to the temperature change, due to the Reynolds number changed as a flow, we're also capturing these particles within the tubing. So cleaning and maintenance of this tubing is important. So we already described the particle loss in tubing, and there are installation challenges, which I mentioned. There are distance between the particle counter and the tubing, necessary bendings and its effect. This is also heavily discussed within this subject. And how many number of bending will be fine? Can we bend the tube for 2-3 times? What will be the diameter and what will be the radius? So these are the main discussions throughout the technical report. And the radius, of course, because if you have a different radius, which are also described in different regulations, we know that there will be a loss of particles within these banding. I already described you the proper using of isokinetic probe. So if idea here, also mentioned yesterday, idea here is to cut the whole column so that the air around will not generate any turbulence, plus you're not collecting the other particles around this area. If it is turbulent, it is fine, because in turbulent air, we don't really need to see a certain amount of air within the air column. But if it is unidirectional, under the unidirectional conditions, we really want to focus on this area without generating any turbulence. These are the two expectations from the regulations. One of them is from the GMP, another is -1, which I already mentioned, the classification. It says that we'll typically no longer than 1 meter in length. Actually, if you are classifying a clean room, especially in at rest condition, I strongly recommend even considering to have your particle counter available on your cart with an isokinetic probe directly mounted for the room, for the corridor, and wherever available for your particle counter to get in. If you're not able to put your particle inside, for example, the machine, make the shortest distance, especially in a rest condition, because there's no operators available, so the room is available for you to make your own study. And if there is operators or any other intervention with your system, then be careful not to exceed this 1 meter, because we had the study, which I will share later on. There are a lot of particle losses in tubing, especially in a spiral fashion. If you're not using any supporting element for your tubing, then you will start losing particles. And in GMP Annex 1, 22 revision, the tube length should typically no longer than 1 meter, unless justified. So if you are able to discuss and justify this by the means of decision tree, which I will share, so that you can directly say, okay, I have these risks that I know, I lower my risk by implementing these features. So the potential solution is the technical report. Keep in mind, 21 is not a standard. It's just a technical report. So it is just giving you a clarification, not as an alternative to whatever we said in -1, but also enhancing the technical, enhancing the standards by offering a technical review. So in this thing, we have the cleanroom classification versus monitoring. We take a look at it in details. In section 5, there are things to consider. One of them is the instrument selection. We know that different instruments are available in the market, so you have to know which one is the best for your application. That's number 1. Number 2, occupancy state and how you will be correlate with these at rest in operation conditions and also as built conditions. So you have to define these conditions to make the necessary design. And sample locations, to select them, it has to be risk-based. But also you have to place them into the right location where you will be able to do your sample. For example, if the risk for the same location, same zone, if the risk is quite similar, then your priority will be placing your particle counter in the easiest point without having the long distance to sample. So this will be your things to consider while selecting the sample locations. And there is an instrument measurement issues. We all know there are particle counters with the limitations. There's a limitation of number of counts per liter. There's a limitations of noise and the coincidence error. So we have to know that these risks are also coming with the system design. So the potential solution, the best piece of the technical report is the decision tree. I will share with you, but before starting this, actually we come from this point. We take this idea and implement it into the technical report, okay? So when we do the decision as an engineers, we always come to the solution. Okay, does it move? If it should move, yes, okay. Should it? No? Then use the duct type to fix it. If it will be on this way, okay, no problem, continue. So this is exactly what we did together with the subject matter expert to see, okay, can we sample directly? For example, if you take a look at here, can you put directly into the airflow? If it's yes, then no assessment required. You can continue. If you connect your isokinetic probe directly to your particle counter, no additional risk necessary. But if you said, okay, I have to have a unidirectional flow, but I'm not able to put my isokinetic probe directly together with my particle counter, then okay, sample tubing is required. So idea behind here, we have this probe orientation as a number one. And the second is the tubing length. So can you do it within a certain distance? If not, then you continue this way. If you can do it, okay, what kind of assessment you need to consider? I have one example that I will go all in detail. I just want to show you after this tube length, we have these tubing bands. And then the decision. Decision takes you to the note number 1, 2, and 3. Number 1, no assessment performed, but we still give you some guidance in terms of how you will maintain your system. Because we all know that the system, even you do the direct sampling, there are something that you need to consider. And note number 2, there are additional assessment that you need to consider because there is a risk at a certain level which will be acceptable in some applications, which not. So if it's not, then additional assessment performed required. So this is the decision tree. This is not a magical thing, but it's good to start with. Let's take a look at it, how we will using it. For example, the probe orientation. You will go with this step number 1, how you will be placing your probe. Okay, can you do the sampling without tubing with direct mount isoprobe to your particle counter? Then if you said yes, you're done. No other evaluation necessary for your system. But if you say no, then okay, the tube length, define it, and we will tell you the potential impact. We take you to the tube length. Tube length, when you come to this point, are you sampling 5 microns? Because the tube length discussion generally comes from the 5 micron particle losses in tubing. 0.5 micron, you are slightly on a safer side of the process. But 5 micron, that's critical. If you said yes, then the step number 3, we will take a look at how many bends you need. Or if you said, no, I'm not sampling 5 micron, then no further assessment required. Reason here is important. Don't forget, all the ISO 14644 standards are for all industries. We know we are trying to capture the pharmaceutical requirement for 5 micron here a little bit, but rest of it, you still have your own risk assessment, which means technical report doesn't give you the full aspect of your industry. For example, we said no further assessment required. You sampled not 5 micron, but the rest is also applicable for automotive industry, for example, because in automotive industry, in paint shop, we have a longer distance tubing where we do the sampling for 5 micron, 0.3 micron, 0.5 micron particle sizes. So if this is the case, for example, then the tube length will not be critical because these are the ISO class 8 clean rooms, then you are sampling millions of particles. So losing a couple of them within the tubing will not really affect you. But maybe in your application, even you are not sampling 5 micron, then you will have a risk. That's why you have to take a look at based on your industry needs. So the step number 3 is the tubing length, the distance. So the question is, can the sample tubing reach using less than 1 meter tubing? If it's yes, then no bending required. If you said no, depending on your distance, you should consider evaluating the impact of particle loss in tubing. Keep in mind, short is better. And also, when you continue with this part, your tube distance and number of bends on top of it will define whether you will be going into the yellow alarm, which is additional risk required, or the red alarm, which means you have to perform additional risk assessment. So, tubing with or without bends. So, can your tubing will be installed directly? For example, can you put your particle right under your machine and one direct tube will be able to connect to your isokinetic probe? If this is the case, then okay, you can do a preliminary assessment of your risk, then you can continue working with this way. If no, then number of bending will decide your risk level. If you can keep it less than 2, equal and less than 2 bends with a certain ready, then you'll be safe. Again, we will be considering to have additional assessment. But if you said, no, I cannot do 2, I need 3 or 4 bendings, then there's a higher risk. So we have to perform the risk assessment in this case. So Remember, the decision tree take us into 3 different steps. One of them was no assessment performed, but we still have an impact of particle losses on our system design. And make sure your particle counter within the risk zone, because you are going to put your particle counter directly into the critical area. In this case, we want to make sure that you have a HEPA filter exhaust, which means your particle counter is not contaminating your environment. And also, particle counter with the isokinetic probe will not interfere with the airflow pattern, which means you're not putting it under the glow area or over the critical location. So you have to pick the right place within the certain distance. Aseptic processing guideline offering us 1 foot away from the risk location, which is 30 centimeter. This 30 centimeter is not just a line. It's like a semi-sphere, so you can have your isokinetic probe a little bit higher than the risk location so that your operator's intervention will not be also change your particle counts. Additional assessments required. Okay, first of all, we need to try changing our design. This is always step number 1. Reason is because we are not dealing with the current new installations, but also looking at the installations that are being installed for a long time, and they didn't really know the risk associated with this system design. So you can evaluate your engineering by changing your design. And define potential impact of current installation and review your alarm and action limit for suitability, which means you can consider changing your alarm and action limit, defining on your risk, and you can make a side-by-side engineering comparison with a portable device to see how many particles are you losing throughout the process. So it also changes the limit. And review your trend data to ensure that the system condition changes are captured. Idea here is, finally, at the end, the idea is to capture the risk conditions. If your trend data will not show you all the risks associated with the particles, then you are at risk. We are not always focusing on the number. For example, in grade A, we said, okay, 100 particles of 0.5 micron and above is critical. But we are not really seeing 101, 102, 103. If there is an alarm, thousands of particles appears. And we are seeing a good peak, which also goes down a little bit every minute. And after a certain minute, we are losing this data. And we are seeing it, okay, within the limits again. So the alarm disappears. But if it's a one-time occurrence, then we already know that from the GMP, this one-time issues can also be acceptable. But 2 things important. 1, this one-time issue is not repeating itself in a periodic way, which means whenever you load your, let's say, the stoppers into the stopper ball, then you get a peak. This is a bad design. This has to be evaluated. This doesn't mean that, okay, this is a one-time issue. But if this happened in a certain moment without any intervention to the system, then you are safe. And we have to consider using the larger diameter tubing, which means we can increase the Reynolds number by changing the diameter of our tubing if you will make more bendings and also the sample points. And maintain and clean your tubing with reasonable time frame to reduce accumulated particles. To clean your tubing, never use the pressured gas. Never use this ultrasonic bath because you are damaging your tubing. The best thing is to fill it with 70% IPA, put it into U shape, and make it like this, a little bit up and down, and let it dry. So with this way, you will be able to clean it up faster and easier. So maintaining should be in the place. For pharma industry, this should be part of the contamination control strategy. Fine, additional risk performed. Exactly the same thing. We will start with the installation design, how we can evaluate it, how we can change our system design, how we can locate the particle counter at the nearest point of our system. And rigid type conduits, such as stainless steel tubing, used to reduce the risk of certain peaks due to the shaking and unwanted contact with the sample tube. This is the one I described at the beginning. Sometimes we are seeing a very long tubing coming along the sample point, but whenever you touch this tubing, you see the peak. So instead, defining your certain radius as well as defining the certain path to sample using these stainless steel conduits are the best application. And again, using the larger diameter tubing is important if you have this kind of a risk. And installation of tools to reduce distance and number of bends like system-made fixtures and apparatus. A specific system apparatus also helps you to take a sample. I have a couple of pictures to show you on this. And maintain and clean your tubing within the reasonable time frame. Again, the particle loss engineering studies performed with same flow rate particle counter assist with the determining particle losses and the degree of risk. So put the particle counter in the sample location. Count the same time period and see how you can correlate these two numbers. Are you able to capture the same risk conditions with the portable device as well as your system instrument? So if you can do it, then you are safe. If you're not able to do it, you might consider finding the percentage of the loss, plus minus, and lower the alarm and action limits so that, for example, your alarm will not be 100 particles per minute. You may say 70, so that the 30% loss considered potential loss also considered with the alarm limit. There are a couple of do's and don'ts for the classification. Always mount your isokinetic probe directly to your particle counter, we already mentioned. And these tubing comes with, each particle counter comes with 3 meters tubing. This is an industry standard for the manufacturers because we are sending it out for different industries. But keep in mind, you have to cut it. And based on your requirement, you have to cut it for the classification. Never use the entire tube alone. And always keep your isoprobe and the tube closed at all times to protect your particle counter from the ambient particle conditions, because we are not always put these particle counters within the clean room. So if they are in the qualification department, for example, don't leave them with the open hose because it will also affect the particle counter. One of the things that I can add, always do the zero count check before starting the measurement, because it is important to see whether your particle counter is counting the real particles or having a technical issue right at the beginning. And don't leave your particle counter on the floor. Most of the marketing material, we are still seeing particle counters lying on the floor. That's terrible. The reason is because the exhaust is also introducing a lot of particles to the ambient air. And do not use tripod next to your particle counter like our marketing team did. You don't need it. Tripods, okay, for critical environment. If you have, let's say, a laminar airflow workbench and have a small entrance, have less than a 1 meter tubing, put this tripod inside, and outside the operator will be active so you can take your in operation conditions. That's a good application, but we don't really need in at-rest conditions within the room with the tripods. And do not clean your sampling tube with a high pressure ultrasonic bath. I already described. Make it a new shape, up, down, let it dry. IPA is the best product for cleaning these tubing. And consider replacing your tubing for a certain period of time. Some of the companies, they're not really cleaning them. They have a certain time frame that they have due date for the tubings, so they are replacing them immediately. So these are the tests we conduct before this event, before the technical report. In 2022, we come up with this testing presentation in ESTEC in the US. And we try to show people the impact of a ship kit. So if you use the ship kit directly, mount it, and compare it with we have a setup here with the polystyrene latex particles. These are all NIST certified cleanroom grade calibration particles for particle counters. So we introduce it to the one particle counter as a test, another is the unit under test and the reference. So the difference between these two, 82.7, which means more than 15% of particles are being lost within the tubing. And with the same way, if you use it with 100 liter per minute instrument, you have 5% loss. Difference comes from, take a look at the same tubing, but the diameter is very thin here, so it goes all the way down. But here, due to the diameter and the thickness of the tubing, it has a very nice curve, see? It maintains a nice curve and it gives us like a 10% difference between these two. Even this is a good example because the tube bending, the shape of your bending, is also causing the lower Reynolds number, which also have your particles tend to stop around the diameter. And these are the bendings, the general. We have this 8 centimeter bending and 15 centimeter bending. According to ISTM F50, 15 centimeter is the best in terms of pulling out the particles smoothly. But unfortunately, if you use this system, for example, in any isolator, you also need almost 15 to 15, another huge area just to turn one cycle. And you need to turn another one underneath, so you need like half a meter area just to turn with 2 shapes. That's why it's not always easy, but we need to see what is the impact of this 8 centimeter bending in your system. So if you use this stainless steel support like this with 2 meters, then there is 11.2% loss for 0.5 micron compared to the reference with 2 bendings only. And if you continue with this bending, which is like 15 centimeter radius, then the loss is less. If you have an available space to make that happen, especially with the longer distance, try to make these bends smooth as possible. One another thing, you don't need to make one full bend. You can make 40° and another 40° so that the air will smoothly move around your system. So these are the applications that we did for the monitoring. Exactly the same structure that are built by the manufacturers of this filling line. We have the same support, and we have a housing underneath for servicing our particle counter. And the opening front, the door, we also changed it so that it's accessible for anyone who needs to reach to this point so that they can take the sample. Or here, we already sampled everything at this point, so the sampling outside of this area is not critical because we're just pulling the air. We're not considering to carry on these particles. But if you are sampling throughout the isokinetic probe, viable or non-viable, you can change this design and evaluate it with this way. And the bendings, remember I said this half bending, 45°, we need to move it a little bit to the needle side, so we make a very smooth way so that we are able to pull out. The loss in this tubing compared to the particle counter side by side is less than 3%. And this kind of installation is helping you to maintain your operators can touch it, or the system will also have some vibration, so you are protecting your system by a rigid conduits. Again, another point, you cannot really leave your particle counter into the surface because there are a lot of mechanical parts underneath. So we have this side installation with a special fixture, and we take it in with a very smooth turn so that the distance is within 30 centimeters from the risk location. Again, another special fixture. See, we have this tubing comes in and supports itself to keep it in a certain distance, which is less than 30 centimeters in this example. And a couple of other installation examples here to protect the system and also keep your sampling point within the risk location. So key takeaways, cleanroom and cleanroom classification and monitorings are not the same thing. We have different regulations. -1 is describing the cleanroom classification. Monitoring is -2 for the continuous compliance. And also the technical report 21 describes both and gives you an idea about how to implement this monitoring system as well as the classification with the sample tubing. Each system has a different dynamics. That's why we're not able to say, okay, this fits for all. It has to be made in a tailored, custom tailor-made systems, and you have to have your process knowledge and the risk knowledge from your setup to locate your risk point for the sampling and also the particle counter. Particle loss in tubing is real. Most people said, okay, we have a tube which is specially manufactured for the particle counters. That's in fact not true, because the test we run was based on these special tubing which has a Teflon inside, silicone outside, but still you are losing particles within it. because the reality behind is the Reynolds number. If you drop the Reynolds number, particles tend to stop and touch into the inner surface of your sample tube. Decision tree is a nice tool to start, but not a permanent solution. So we have to know that it's a good point to start with, but your industry requirement also define the rest of the process. So this is all about my presentation today. If you have any questions, I'll be happy to answer.
Thank you, Hasim. That was very comprehensive.
You're welcome.
Very comprehensive. Anybody got any questions? We've got a couple of minutes before the next talk. So, oh, there's a hand up. There you go.
Hello, David Mitchell from Biosynth. I've come across a number of auditors that when we have looked at that 30 centimetre gap have absolutely gone ballistic and basically said, no, do your risk assessment and work out exactly where you need it. And actually, when I've sat with them and gone through it, they've allowed me up to 45, even 50 centimetres from what they would consider, because they actually said you've got to balance the risk of where your tube is and interference as opposed to what it is you're actually trying to capture. So I just wondered where that 30 centimetres was coming from.
So this 30 centimeter comes from the FDA aseptic processing guideline. There is a sentence saying that 1 foot away from the risk location is the good point for particle monitoring. This is where we referenced. But also, as a distance-wise, when you have your risk location, let's say in pharma, the turntable, or in the filling nozzles, you have to be close as possible. In some cases, I agree, there is a distance where you are not able to place your particle counter within the 30 centimeter from the risk location. But in this case, you have to justify it with your at-rest data that you are collecting from this location and saying that your sample point selected is also representative to the compared with the engineering study that you made with the portable device. So with this way, you can also justify. We have a couple of locations where we are not able to put our isokinetic probe nearby 30 centimeter. So if it's more than this, we still need to make some justification. There are a lot of magical numbers in our industry, 0.45, 20 air change per hour, and this 30 centimeter distance. They're all coming from one point. Exactly the ISO class 5, 3520 comes from the same, because when NASA said, okay, let's keep it 100 particles in feet cube, then this 100, nobody really say anything, then this 100 become an industry standard in all Europe now, because they just multiply it imperial to the metric. Then it makes them 3520. So we always have this initial value, but the standards are also moving into the risk-based approach, which means we are not sticking to these numbers like your presentation yesterday. We're not sticking this, but we are also justifying it with our risk assessment. That's why we still use this 30 centimeter, but all the post and pre-risk assessment file, we're also making a justification on our locations.
Any more questions? No? Oh, go on. Go on.
Yeah, very last minute.
That's a very quick one, just about materials of construction, because you mentioned about bends and diameters and stuff like that. And I think you mentioned stainless steel, maybe for tubing. So are there any specific materials of construction which are ideal that you minimize the dropout of particulates in long lengths?
I saw direct stainless steel tubing connections, which worked very well with the passivation in it. And of course, there could be other things, because idea is to bring these particles from the source all the way to the particle counter without introducing extra particles, plus without losing them in the tubing. So there are different materials that are being tested, but the best practice in industry nowadays is the sample tubing that we are using, because they are very good at collecting particles and not adding more into it. But I saw direct stainless steel connections that people used, especially for the lab environment. So maybe in the long run, we will be seeing this specific tubing as well.
Thank you.
You're welcome.
Excellent. Thank you, Hasim.
Thank you so much.
Thank you for that.
Thanks for listening.